In this video, we're going to go over binomial probability distributions along with a few examples. So first of all, a binomial probability distribution is characterized as an experiment with the following conditions. So first of all, you have an experiment that is repeated n times. Also, the outcome of each trial consists of only two possibilities. You either get a success or a failure. Also, the probability of success, call it p, and the probability of failure, which is going to be 1 minus p, must stay the same for each trial. The trials must also be independent, meaning that the outcome of one trial doesn't affect the outcome of any other trial. And the random variable x that we use will represent the number of successes in the n trials. So that's what a binomial experiment is. These conditions define a binomial experiment. Now let's take a look at the binomial formula. Now let's take a look at a few examples illustrating these conditions. So for the first example here, we have a coin that's flipped 10 times, and we note the number of heads occurring in the n trials. Find the probability that in 10 coin flips, 4 heads occur. Now this is an example of a binomial experiment. Now in this case, we notice that the number of trials is 10, so that's what the n is going to represent. N is the number of trials. And we get that from the fact that the coin is flipped 10 times. Now, in the problem, it's also stated that we want to look for the number of heads that occur. So that means a success is getting heads when you flip the coin. So that's what we consider a success. The probability of success, p, is 1/2, and the x that you're looking for is 4. We're looking for the probability of getting 4 heads in 10 coin tosses. Now we're going to calculate this probability later on. We need to go over the binomial formula first, and then we can calculate that probability. But this just illustrates an example for a binomial experiment. Here's another example. So here we have a company that makes eyeglass frames, and it's been noted that 98% of the frames produced are acceptable. A quality control engineer selects 100 glasses at random and tests them. Find the probability that 3 eyeglasses in the 100 selected are found to be defective. So in this case, we have n equals 100. That's the number of trials. A trial is where the quality control engineer selects 1 eyeglass at random. And he's doing that, and they are doing that 100 times. Now in this case, a success is actually getting a defective frame. So that's what we consider to be a success in this case. A success doesn't necessarily mean a good thing for these problems. The probability of success, that is getting a defective frame, is 0.02, so that's what our p is going to represent. We get that from 1 minus 0.98. And then we're looking for getting 3 eyeglasses, and we are looking for getting 3 defective eyeglasses in the 100, so our x is 3 in this case. So this is another example of a binomial experiment. Now let's take a look at our binomial formula, and then we'll do a few examples. So here's our binomial formula for calculating the probability of x successes in n trials. It's a fairly simple formula to follow. So the probability of getting x successes in n trials for a binomial experiment is simply this. We calculate ncx, multiply by p to the x power, multiply again by q to the n minus x power, and that is our probability for getting x successes in n trials. Let's go back to those examples that we saw previously and calculate the probabilities now. Now here are our two previous examples. So the first one, remember, we were flipping a coin 10 times and noting the number of heads that occur. We want to find the probability that in 10 coin flips, 4 heads occur. So here's our binomial formula right here, and we have to identify the n, the x, the p, and the q, and then just plug everything in here and evaluate it. So in this case, the total number of trials, that's 10 because we're flipping the coin 10 times. We have to decide what a success is. Well, in this case, we're going to consider a success as getting heads. Then the probability of a success in an individual trial is 1/2. The probability of failure, that's going to be 1/2 as well, because remember q is 1 minus p. And if p is 1/2, then q is also 1/2 in this case. And the number of successes we're looking for is 4. So we just plug everything into our formula right here, and we get our answer right here that we have to evaluate. So we get 10c4 times p to the 4th, 1/2 to the 4th, times q to the 6th, or 1/2 to the 6th power. Notice 10 minus 4, that's where the 6 is coming from. Now we can use a calculator to evaluate this, or Excel, and we will get 0.205. Now there's also a built-in Excel function that allows you to plug the information in and you'll get back 0.25 very quickly that way. Let me show you how to do that with Excel. So here we have an Excel spreadsheet. Just pick any cell, and if we type in equals binom, you see you get your binomial distribution appearing here, tab. Now it tells you what to enter. The number S that you're looking for, the number of successes, you see number / S. So we want 4 successes in this case. The number of trials is 10. The probability of a success is 0.5 in our case. And for the last argument, that can either be 0 or 1. In this case, we want it just to be 0. 1 would give us a cumulative probability distribution. And there's our answer, 0.205. Now let me talk a little bit about that last argument. Bring that equation back up there. You see this 0 right here. If we had changed that to a 1, then we would have had a cumulative probability distribution. What that means is that when I hit enter, it would give me back the probability of getting either 0 heads or 1 or 2 or 3 or 4. So it would add up all the probabilities from 0 through 4. So that would be our cumulative probability distribution. And we'll use that in another example later. But for right now, for these problems, we just want 0 there for our regular probability distribution. Remember, the 1 will give you the cumulative probability distribution. And there you go. That's all you have to do. Now notice we could have entered the formula NCX, so I could have typed in combin 10, 4 times 0.5 raised to the 4th power times 0.5 raised to the 6th power. That's using the binomial formula. and we will get back the same answer that we have in this cell right here, 0.205. And you see that's exactly what we get back. So this one right here is using the full binomial formula where we type it in by hand. And this one is using the Excel built-in binomial function. Now here was our second example that we looked at. So remember, in this one we have an eyeglass company that makes frames, and it's been noted that 98% of the frames produced are acceptable. A quality control engineer selects 100 eyeglasses at random and tests them. Find the probability that 3 eyeglasses are found to be defective. So in this case, our number of trials is 100. Each trial is selecting 1 eyeglass frame. A success we're going to call getting a defective frame in this case, because we're looking for the probability of getting 3 defective frames. So we'll consider a success as getting a defective frame, in which case the probability of success is 0.02. That comes from the fact that 98% of the frames are acceptable, so 2% are defective. So if you reach in and grab an eyeglass at random, the probability of getting a defective one is 2%, or 0.02 probability. The probability of failure is getting a good eyeglass frame, so that's 98%, or 0.98, which you also get by going 1 minus p. And the number of successes we're looking for is 3. So there you go. We have n, p, q, and x. We just have to plug them into our binomial formula right here, and here is our answer. 100c3, that's the ncx, p to the x, q to the 100 minus 3, or n minus x. And if you evaluate this on a calculator or Excel, you will get 0.182. Of course, you can also use the built-in binomial dist function that's available in Excel, and you would type it in right like this. Let's just do that and see that we get back 0.182. So I'll just select a cell somewhere, and we just type in equals binom dot dist. Okay, so the number of successes we were looking for was 3. The number of trials was 100. The probability of success was 0.02. And we do not want a cumulative probability distribution in this case, so we put a 0 there at the end and hit enter. And there you go, 0.182. And that's our answer. And remember, you would get the exact same thing if you type that formula out by hand using the combin function first. 100, 3, p to the x power, which was 3 in this case, times 0.98 raised to the 97th power. And you see we get the same thing. Here's another example. For this problem, we roll a 6-sided die 10 times, and we note the number on the side face up. Find the probability that 3 4s are observed. Alright, so for this problem we need to identify the n, the p, the q, and the x. Well, we see that we are rolling the die 10 times, so that's our n. Now, what do we consider to be a success? Well, we're looking for getting 4s on the side face up, so we'll consider getting a success to be a 4. So our probability of success is then going to be 1/6. Then our probability of failure is not getting a 4, or 1 minus 1/6, which is 5/6. And then the number of successes we're looking for, of course, is 3. We're looking for 3 4s. So then we just have to plug all this information into our binomial formula and write down here is our answer. NCX, so 10C3. This is P to the X power, 1/6 to the third. And this is Q to the 10 minus, and there should be a 3 right here. So this is going to be a 7 in the exponent right here. And that's going to be your answer. And of course you can just use the binomial function built into Excel. Here's how you would type it in. 3, 10, that's x, n, comma, and then p is 1/6, and you do not want a cumulative here. Remember, if you put a 1 there, that would give you the probability of getting 3 or 2 or 1 or no 4s appearing. So we don't want that. We just want to know the probability of getting exactly 3 4s. And so we put a 0 there and type that into Excel, and you'll see that you get back 0.155. So for this problem, we have 5 flights daily from Pittsburgh via U.S. Airways into the Bradford Regional Airport. Suppose the probability that any flight arrives late is 0.2. So we have 2 questions here. What is the probability that 2 of the 5 flights are late today? And then part B, use Excel to create a table representing the probability distribution for the random variable x that represents the number of late flights on any given day. So for part A, this is our solution. So n is 5. That's the number of flights arriving in a day. We want to find the probability that 2 of them are late, so x is going to be 2. Remember, we're considering a success to be getting a late flight. The probability of success is 0.2, 20%, and the probability that a flight is not late is 80%, or 0.8. So the probability of getting 2 late flights by the binomial formula is going to be 5c2, that's ncx, you see the n and the x, p to the x power, 0.2 is p, the x is the 2 right here, and then q to the n minus x, that's 5 minus 2 right here. Evaluate this on a calculator or Excel and you will get 0.205. And that's just a coincidence that that is the same number as one of our previous answers. Now for part B, we're going to create a probability distribution, so we're going to use Excel. So here's the table that we're going to create. This is our probability distribution right here. And the way we can create this with Excel is by using these formulas that we have right here. So let me show you how to create this in Excel. So let's pull up Excel here. Now X is going to represent the number of late flights in a day. So that can vary from 0 to 5 because there are at most 5 flights in a day. Now what's going to go in this cell is the probability of getting 0 successes in 5 trials. In other words, getting 0 late flights arriving on a day. So what we're going to type in here is equals now we want to put in 0 in here. Now that's in cell A2, so I'm going to type in A2. The number of trials is 5. That doesn't change. The probability of getting a late flight is 0.2. And we do not want a cumulative distribution here, so we put 0 there. and we hit enter, and there you go. Now all we have to do is grab that fill handle, drag down, and here is our probability distribution. So each of these numbers represents the probability of getting X successes. So for example, this number right here is the probability that on any given day, 3 of the 5 flights are late. So that would be about a 5% chance of occurrence. Now, just to make sure that this is a probability distribution, that we did everything correctly, we should be able to sum these up and get 1. So let's just check that out. And yes, they do sum to 1, so looks like we didn't make any errors. So there's our probability distribution that we created on the previous slide. Now in this example, we're going to use the cumulative binomial distribution. So for this problem, we have a study by the Illinois Department of Transportation, and they've concluded that 76.2% of drivers use seatbelts. Now we have a sample of 12 vehicles is selected at random, and we have these questions. So the first question is, what is the probability that the drivers in exactly 7 of the 12 vehicles are wearing seatbelts? Part B, what is the probability that the drivers in at least 7 of the 12 vehicles are wearing seatbelts? And then part C, what is the probability that between 5 and 10 of the drivers of the 12 vehicles are wearing seatbelts? So let's take a look at the solution to part A first. Now here's our solution to part A. So in this case, the number of trials is 12, so the n is 12. Now we're going to consider a success to be finding a driver wearing a seatbelt. So our x is going to be 7. We wanted to find the probability that 7 of the 12 drivers are wearing seatbelts. Now since a success is finding a driver wearing a seatbelt, the probability of success is 0.762. Remember, the problem said 76.2% of all drivers wear seatbelts. And the probability of failure is going to be 1 minus 0.762, or 0.238. So now we just have to plug everything into our binomial formula. So the probability of finding 7 out of 12 drivers wearing seatbelts is going to be 12C7 times 0.762 to the 7, that's p to the x power, times q to the 12 minus 7, or 0.238 to the 5th power. And if you evaluate this, you will find that you get 0.09, so 9% chance. And if you used Excel, you could just evaluate this using this formula right here. So that's the formula that you would type into Excel. Note that you have a 0 right there at the end. Now in parts B and C, we'll see we actually want to use a 1. Now for part B, recall, we wanted to find the probability of finding 7 or more drivers wearing seat belts. So that's what this represents, the probability that x is bigger than or equal to 7. Now, if we want to use Excel, Excel doesn't evaluate this directly for us. We have to do it a little indirectly. So notice that the probability that x is bigger than or equal to 7 is going to be 1 minus the probability that x is less than or equal to 6, right? You see, if I say x is bigger than or equal to 7, the complement of that event is x is less than or equal to 6, right? That's the complement. If this is event A, the complement of event A is getting 6 or fewer drivers wearing seat belts. So therefore, the probability that x is bigger than or equal to 7 is going to be 1 minus the probability that x is less than or equal to 6. Now this part right here, we can evaluate using Excel. Excel has a built-in function for that. And right here it is. So to evaluate this in Excel, we just type this formula right here into Excel. So that's what we would type into Excel. So 1 minus, now let's take a look at this formula. So we type in binom.dist 6, that's this 6 right here. So this 6 right here is this one. 12 is the number of trials. 0.762 is the probability of success. Now notice we put a 1 here now instead of a 0. That will give us a cumulative probability distribution. So by putting a 1 here, this gives us the probability of 6 or fewer. And so what we have is this part right here is exactly the probability that x is less than or equal to 6. And that's this piece right here, and we go 1 minus that, and that will give us our answer. So if you type this into Excel, you'll see that you get back 0.9563. And that's your answer. Now let's take a look at part C. Now for part C, we wanted to find the probability of getting between 5 and 10 drivers wearing seat belts out of 12, inclusive, meaning X can be 5 or 10, or any number in between. So we want to evaluate this probability right here. All right, the probability that X is greater than or equal to 5, less than or equal to 10. Now to do this using Excel, we're going to have to break it up like this. Notice that the probability that X is between 5 and 10 is going to be the probability that X is less than or equal to 10 minus the probability that X is less than or equal to 4. You see, what we're doing here, think of it like this. Say this is 0, 5, 10, and then here we have 12. So the probability that X is less than or equal to 10 is this. Think of it like this. It goes from 10 down to 0. And then the probability that X is less than or equal to 4 would go from here down to 0. And so when we subtract these two, what we're going to get back is this probability right here, the probability exactly from 5 to 10 when we subtract them. You see, when we subtract this from this, it's taking away this part right here and leaving us with this probability, the probability that X is between 5 and 10. So that's what we have to evaluate. So now to evaluate each of these using Excel, we can use the cumulative binomial distribution. So this piece right here is entered like this. Once again, notice that we have a 1 right here. So that will give us the probability that X is 10 or less. And then the probability that X is less than or equal to 4 is this one right here. And notice we also have a 1 here. And if you were to type this into Excel, you'll find that you get 0.8161, and that is your answer. And so that's how we can evaluate probabilities using the cumulative binomial distribution feature in Excel. And that concludes our discussion about examples using the binomial probability distribution.